Okay, this is a special kind of problem that presents a little bit different difficulty. Now we have a man standing on an elevator. Now if the elevator is not moving, then the scale that he stands on will read his weight because there won't be any other force operating on him. Unfortunately, in this problem, in the first instance, on the A side here, he's now moving up at a speed of 1.2, acceleration of 1.2 meters per second squared. So this generates an upward force shown here and also shown here, which has an equal and opposite downward force exerted by his body in response to it. And then there's a second, if we, instead of accelerate, we are now having a velocity of 1 meter per second upward. So let's take a look at how we would do the calculation of these two situations. First of all, he's moving up at 1.2 meters per second squared, and he has a mass of 75 kilos. So the force exerted here is going to equal the multiplication of that, which is 90.0 newtons. His weight, when this is not moving, is 75 kilos times 9.8, which is 735 newtons. Now what happens when this is moving up? There's an additional force down in addition to his weight, which is the equal and opposite reaction to the upward force that's causing him to move up. And that's what presses on the scale. So the scale is going to read 735 newtons plus 90 newtons, or 825 newtons. So that's the first situation. The second situation is a velocity of 1 meter per second squared, but there's no change in velocity, so there's no acceleration. So A is equal to 0. Therefore, there's no force exerted other than the force of gravity. So the scale is going to register the same, which would be 735. We will talk about this in the future when we talk about electric forces, but when you have a positive and negative particle that come into the same area, the field that results causes an attractive force between these two particles, and there is a way of calculating the attractive force that occurs. Also, there's the possibility of an exchange here, an exchange of forces and an exchange of masses that occurs. In the first situation, or first diagram here, you have the person exerting F1 and propelling the ball in this direction with this force, and he is equally and oppositely pushed on by the force as well. When the ball arrives and he pushes it back, he also institutes a force and pushes it back in the other direction. He has to do that in order to catch the ball, and so he is catching the ball, and at the same time, and assuming no friction, these forces have to equal each other, and they will feel the same in each direction. An analogous exchange here occurs when a proton exerts or exchanges a meson to a neutron, and it's exactly the same as if this guy throws a basketball to this guy. And the force exchange that occurs is exactly the same. So let's look at something in review now. Here we have a rocket-powered sled that we've seen before, and it is accelerating at 198 meters per second. It has a mass of 2,100 kilograms and a friction force of 650. What is the force leading to deceleration? So if it's being decelerated at a rate of this amount, what force is responsible for decelerating? Now this is kind of an interesting question, because what you have to say is it both the force that's causing this deceleration, is that taken into account friction, or is friction on top of whatever that force is? And so this question is actually not as well stated as it should be. That being said, let's do the... So we have a rocket sled that's decelerating at 196 meters per second squared, and the mass involved is 2,100 kilograms, and the friction force is 650 newtons. And so the force required to do this deceleration is going to equal the mass times the deceleration, which is a very large number, 41,600. Now the question is this friction incorporated in here, or is it in addition to that? And the question's not entirely clear about that, but I went ahead and assumed that it actually was not included, and so we would subtract this from this, and you would get 41,950 newtons. But I wouldn't give you a problem like this, because I don't think this problem is very well stated. Now let's take a look at another problem involving this guy. Here now we have the sled is now accelerating at 49 meters per second squared. A passenger has a mass of 75 kilograms. What is the horizontal component of force of the seat back on the passenger? Now you'll notice that the sled mass is not given. And the question you're thinking is, well, is it the same as before, 2,100 kilos? You also notice that although it's pictured here, the friction force is not given. And again, you're thinking, is it the same? Actually, it doesn't matter, because the system only takes into account the person and the back seat of the sled. The person is accelerating, and the sled is accelerating at 49 meters per second, and the person is accelerating at 49 meters per second. And that's what's important, because the force that's accelerating him is what's pushing on the seat back, and so that's what he's going to feel. So let's take a look at what that means. So since we're only taking into account the person, then the force on the seat back is going to equal the 49 meters per second squared acceleration, and his mass of 75. So the force on the seat back here is going to be 3,675 newtons. And it doesn't matter how much the sled weighs, it doesn't matter how much the friction force is, because it's it's similar to the problem we had with the professor and the cart, where when the system changed, then the whole situation changed, and you didn't have to know or have to take into account that other part. But this is the force that the seat back has to push on his back in order to have him move with that acceleration. Now here's the last slide in our group, and the last problem. We have two children that are pulling. You can't see them, but they're pulling. You have a child sitting in this, and they're pulling him in this direction, and at the same time there's a friction force of 7.5 newtons in this direction. This child is pulling at 10, and this one is pulling at 8, and here's the angles involved, and here's the free body diagram. Now the question is, what is the acceleration if this child weighs 49.00 kilos given this situation? I got myself a new piece of paper here. What we have is the friction force is going this way at 7.5 newtons. We got one kid pulling like this at 10 newtons. Now one kid pulling down this way at 8 newtons. The resultant is out this way. This angle is 45 and this angle is 30. Now in both cases it's the x component here that's important, and so what we have is this 10 times the cosine of 45 plus 8 times the cosine of 30, and that's going to equal the x component of what the kids are generating, and that's going to be opposed by the friction force, and then whatever's left after all that. So 10 cosine 45 is 0.5 plus 8, and the cosine of that is 0.707 minus this friction force is 7.5, and if you do all this you end up with the force that generates the acceleration, and when you do that you get 6.5 newtons, and then that is going to this 49 pound or kilogram kid. So to get the acceleration, you realize that F is over m is equal to a, so that's going to be 6.5 divided by 49, and so his acceleration is 0.133 meters per second squared. Okay, that finishes up our lectures for this week. If you have any questions about the homework, obviously you'll bring them into class and we'll work through them in class. And hopefully this will help you understand previous lectures as well in terms of dividing things into the x and y component. I want to thank you for your attention.